to make a quick, and I'll make a quick announcement over in Slack so we can hurry people over here.
Okay. The YouTube stream is live. We're recording. I think. Professor Max Donlin will be chairing this session. Take it away.
All right, well, I'd like to introduce the first speaker, which is Pranav Bhounsule from the University of Illinois at Chicago. I'll let him introduce the title of his talk. Welcome, Pranav.
Thank you, Mike. Thank you, Chris. Sorry. Okay, can you hear me?
Yes.
Yeah. Okay. Great. Should I just start?
Take it away.
Please start.
Okay. So this is preliminary work, and I would like to get your feedback on my talk and in general the ideas. So I'm going to start off with some basics on dynamic walking or locomotion, and this is only for newcomers. When we think of robots with point feet, we can't control them instantaneously, but we can control them over a time scale of a step. So the idea is here is if you have initial conditions shown by the star, and if you integrate that initial condition or take the robot from that state, which is at a certain section called the Poincare section, could be the apex or heel strike, it follows this red trajectory. And if you're back to that same initial condition, x0, then that's called a fixed point, and this particular red line is called the limit cycle. So you can write this as this equation on the right. X0 is the initial state, U0 is the parameterized control. And if you get these conditions right, you end up back at the initial state, x0. F is called the Poincare map. And only for simple systems do you have an analytical solution. Most of the time, you do not have one. You need to integrate the equations of motion to get that. So next we come to the problem of stabilization, which is if you have a random initial condition xi, and you want to do something with your control ui so that the next step you're close to x0, which is your fixed point. How do you do that? That's the problem of stabilization, and that's going to be the focus of my talk today. So one way of doing that is, and this is really demarcating the ways based on how you use the model F. One thing you could do is you could formulate an optimization problem, as we've seen in other talks. Here, the cost is given here. It consists of deviation from the nominal in terms of state, a deviation from the nominal control. Q and R are design matrices, and these are user choices subject to the model. So the model here is a linearized version of F. So what you do is you take the gradient of F, which is the Poincare map as a function of state and of controls, and that stick that A and B here. And you can solve this optimization problem using your favorite solver. It's actually a quadratic problem, and it's fairly easy and fast to solve this. Now, the issue with this formulation and the ensuing solution is that this is very computationally efficient because it's a linear problem, but it results in a small region of attraction. A region of attraction is the set of initial conditions which would eventually end up at the fixed point. And that's because this A and B are valid for a small deviation in state or controls. That's method one. The second method, which is using a nonlinear model, formulates the same problem, same cost. However, use the nonlinear model. And here F is obtained by the set by numerical integration. When you solve this problem, the same problem with the nonlinear model, you end up with a large region of attraction because F now represents the all possible states, and it's more complete than the linear model, and hence you get a large region of attraction at the expense of being computationally inefficient. And when I say computationally inefficient, it means that it's going to incur a time to actually do this computation if you want to do this online. So here's the key idea, and I'll come back to why I'm doing this a little bit later. So essentially it's the same optimization cost, but now we like to see if we can approximate F, the Poincare map, with some closed form approximation. And the reason we want to do this is because I want to be able to achieve a large region of attraction as well as make the optimization fast enough that I can do real-time online optimal control. Now, people have done this before. They would take the special system, in this, usually it is the one which the solutions are available are rimless wheel and simplest walker, or for a hopping model, the spring-loaded inverted pendulum, you can do certain linearizations and get this map analytically, but most cases you can't. And especially for a more complex model, you just can't get a analytical solution. So this is hopefully a method which will work for almost all models, provided you have a simulator available which can give you F numerically. So there are essentially 3 steps. First, you generate data. So you put in all the possible inputs, initial states, all the controls UI, and these are represented as the blue dots. You put them in the simulator, you integrate for one step. Some of these trajectories will fail, some of them will succeed, and end up with the red dots, which are your outputs. And once you have this data, inputs and outputs, the second step, fit this data with your favorite regressor. So F here is now I've written down as F bar, which indicating that's an approximation. You could use a polynomial, you could use neural network, parametric or non-parametric, that's your choice. Ensure that you get a good fit, of course. And once you do that, now you're ready to solve the optimization problem. Again, now with this approximation. Okay. Now my hope is that if I do this right, then I'll get a large region of stability or large region of attraction, and hopefully it'll be completely efficient. So this is a toy model in which I tried this. It's the spring-loaded inverted pendulum of running. The model starts in the apex. When the vertical velocity is 0, there's a touchdown, and then there is takeoff. It ends up back at the apex. The states at the apex are the velocity, the horizontal velocity, and the apex height. And the controls are just the foot placement angle. Okay, so can we increase the region of attraction for this particular model with this approximation? So I'm going to show a plot of, well, 5 plots here, but let me start off with this plot, F integration. This is a plot of X dot on the X-axis and apex height on the Y-axis. These are all initial conditions in which you start the optimization and see if the robot falls or doesn't fall after 5 steps. Now you could choose 10 steps, 20 steps, but 5 steps seems to be good enough to say that the robot will fall down or not. So each of these blue dots are the ones which I tried doing this for 5 steps and saw if the robot fell or not fell. And if it falls, then I show it with a white region. If it does not fall, it's in the region of attraction. That's shown by the gray area. So F integration uses the integrated model, the exact model, so to say the ground truth. The red is the fixed point, and so you can see that it almost covers the whole area I started off with. With the use of linearization, the A and B matrices, you end up with a smaller region, and the plots down show 3 possible approximations. F is quadratic, F is a Gaussian regression, which is a nonlinear parametric model, and then if F is a neural network. So each of these are better than the linearization, but not as good as the integration, but they're quite close. So for example, the neural net and the quadratic approximation surprisingly give a very good stability in this case. So the next argument is this computationally efficient? In case of step-to-step control, what we're trying to achieve is we have more time than it's available in traditional continuous control. We actually have time from the apex almost the stance to actually make a decision to swing that foot and place it the right place. So for all these 5 models, it turns out that it's almost constant, 350 milliseconds. That is, it takes 350 milliseconds for the robot to go from apex to touchdown, and that's the time available for foot placement. So this plot on the right shows the computation time. Clearly the red, which is the linearized model, is very fast. It's few milliseconds. Next is a polynomial, and next is Gaussian. And these 3 have time less than 350 milliseconds, which means that if you use this real time, the robot has enough time to make that choice and place the foot. But the neural networks does worst. And then of course the simulation, which takes twice as much time. So this probably shows that using approximation, you can actually get this computation done in real time for online implementation. So to give the big picture, this talk was essentially about approximating F, the Poincare map. Hopefully, with this simple example, it can be seen that this leads to a large region of attraction and essentially fast computation. One of the facts which I exploit, and this is true but never really seen carefully, is that F is actually a smooth function of the parameters, unlike the continuous dynamics which are non-smooth. We also found that if you have a 90% accuracy in your approximation, you usually get good results. Like all the results here had a 90% accuracy in terms of computing F. And the good thing is that you can now use a black box simulator to get F. You don't really need to exploit the structure of the model or anything like that. Some other ideas which I have not explored, but I think potentially could be explored is, since you have analytical F, or so to say closed form approximation, you can then start computing the Jacobian Hessian of F. And this can be used to speed up optimization. The optimization I showed you did not do all those things. And it was also done in MATLAB, which is quite slow. So using C and things like that will make it much faster. The other thing which I've explored and not shown here is if you approximate F as a polynomial, then you can actually use sum of squares to find the region of attraction, which I've not done here. In this case, I just used simulation to find the region of attraction. Two limitations which come to the mind is this scalable? I think for large X, large U, there's large number of parameters, this may not be scalable. But one good thing about legged robots is that the falling dynamics are essentially low dimensional, usually 3 or 4 dimensional. So it might as well scale for legged systems, not for maybe other systems. And then finally, this method is essentially sensitive to the control parameterization. So if you have a control parameterization which leads to quick divergence or leads to many failed states, then this is going to doom. So you need to be thoughtful about what parameterization you use. In this case, I used a parameterization which is the foot placement angle, and that worked well. So to summarize, here is the big picture. Generate the data from using a simulator, fit the Poincare map with a suitable regressor, and then use that map for control using whatever method you want. Here I used optimal control using a simple quadratic cost. With that, I'll end my talk. I'll take any questions.
All right, thanks, Pranav. 214 people are clapping in various countries. So if you want to ask a question, Pranav, you can raise your hand in the participant list somehow. I don't see any. Yeah, okay, I see people raising their hands, which is great. So let's start. I don't know how to navigate that exactly, but Hansel, I saw you were one. So would you like to unmute your mic and ask your question?
Yeah, sure. Do people hear me?
Yeah, I can hear you.
Okay. So you said for the nonlinear model, it has larger region of attraction than the linearized model.
That's right.
And, well, I can tell that they would be different, and some other approximations may lie in between them. But for me, it's not straightforward that nonlinear model always has larger region of attraction. Is it always true for any kind of system?
Well, at this point, I wouldn't generalize to say that a nonlinear model has to have a large region of attraction. It's accepted that if you have a perfect model and if you use the perfect model to do perfect control, in this case optimal control, then you will definitely get, a large region of attraction, assuming that there is that region of attraction available. In the sense, your system is not hopeless that you can't do things with your control. And this is going to be very case specific. What I've shown here is for one model with very limited control. It only can control the landing angle. So it can only effectively control, it cannot control the energy. It cannot input or subtract energy because it's a conservative model. It shows a big region of attraction. So I'm hopeful that if you take something else, it will work. But this is not, I would say this is not a fundamental. We may not get these results for other systems, and so it needs exploration.
All right, great. I'm just going to work my way down the list. I think it's sort of in the order that the hand was raised. So Andy, you're next.
You do an optimization on this quadratic cost, and then you evaluate the quality of your control by the basin of attraction. Why not just more directly optimize on the basin of attraction, or perhaps even instead of optimizing for quadratic cost, do something even cheaper, like optimize for how close you can get to your fixed point in one step, and then and skip the quadratic cost altogether.
Oh yeah, this is
Chris hasn't answered the question. I can just see by his facial expression.
I just used the quadratic cost to show one specific example, but you're right. You could take you could just optimize based on basin of attraction. You could take all initial conditions and then say what's the control which minimizes all of them. That's definitely a way. I just showed it as a way to demonstrate if you keep the cost same, you use different approximation, then this is what you get. But other ways of finding the control are absolutely valid. Does that answer your question, Andy?
Close enough.
And Manoj is not raising his hand, but asking it independently, like on the chat. And he says, the basin of attraction should not depend on the cost minimized. Just for getting on the record here. Chris, you want to ask your question?
So I think this is a little misleading in that you're basically saying we can control anything. And it doesn't really matter how you parameterize the model. And it doesn't really matter how you parameterize the controller. And theoretically, yeah, that's true. And yeah, the basin of attraction doesn't matter on the cost and anything else. But in practice, it's definitely not true. And one of the reasons is modeling error. We could have unmodeled dynamics that your X might not be complete. And the other is that I'm going to use the term singularity, but essentially it's any time that the mapping sort of changes curvature very quickly. And that is going to introduce control problems. There are limits to practical gains you can have. And the mapping induces a gain that is higher than it is possible to implement.
I fully agree. I mean, this is just a start. There are great ideas to explore. That's all I can say at this point.
Well, I mean, you could run these things with some kind of H infinity ball and say, this is my uncertainty in the frequency domain, and basically locally linearize, and it'll tell you whether you can stabilize that or not.
Yeah. But that's true. I mean, I fully agree with you.
Okay. Let's get Shai to ask his question, and then we'll move on to the next speaker, I think.
So I guess it's a question and a quick note. So you had noted that this map is smooth for one-legged impact. That map will always be smooth. That's just a feature of the system.
Mm-hmm.
And that's why you sort of expect your quadratic optimization approximation to work pretty well. But I did also want to ask and maybe point out, I like the fact that the quadratic gives such a good result. That's actually pretty nice to see. There's this notion of stochastic linearization that, at least to an extent, can also be extended to higher order polynomial approximation, where instead of trying to approximate the response for specific inputs and outputs, you take a probability distribution of states and you try to make something that's on average correct in the region, which would still give you a pretty concise low order model. Have you considered trying that as an approach?
No, I've not, but this gives me good ideas on how to maybe do a stochastic optimization here. I've not explored those things, no.
So there is a control theory literature on stochastic optimization that might be useful for this.
Thank you.
Stochastic linearization, yeah.
Okay, in the spirit of dynamic walking, I feel like I maybe cut off the exchange between Pranav and Chris Atkinson a little early. And I wanted to circle back to that to make sure that you guys are satisfied that with responses and answers, and that Chris, you made your point and so on.
I didn't really understand the discussion, so if someone would translate it for the rest of us, that would be good.
Chris may have left the call.
Oh,
So-
he's left.
So Pranav, why don't you, do you want to translate what Chris was saying?
Well, I believe this is my understanding. He's saying that I believe he's saying that this. I just lost my thought on this. He basically said it doesn't matter. That's what he's saying. That this approximation doesn't matter. He doesn't think that approximating it as any of these would eventually give you anything. That's what message I got.
I guess
Okay,
I would
maybe
translate
we'll,
it as saying that you're sort of approximating the true or the nominal function here, but missing the noise aspect or the uncertainty aspect. And that his claim was that maybe the uncertainty is more important than a better approximation of the nominal function. That's at least my take on what Chris said.
that was helpful. Thank you. Okay, well, let's move on to the next speaker. Thanks, Pranav.
Yeah, thank you.
Again, thousands of hands clapping. So the next speaker is Anna, who's going to be talking about shear wave tensiometry. And I'll let you introduce it more. Thanks, Anna.
All right, thank you so much. Can you guys see my screen okay?
Yes.
Great. So several studies have shown older adults use less ankle power and work than younger adults, and this discrepancy becomes more apparent at faster walking speeds. However, the causes for this reduced power output in aging are not completely understood. There are well-studied mechanical and neural changes to the underlying triceps surae musculature that influence power output. I've noted a few on the slide, but ankle power only provides information on the net effect of muscle tendon actions and cannot provide insight into the work done by the triceps surae itself. Therefore, the purpose of this study was to investigate the modulation of force and work done by the triceps surae across walking speed. We used the recently patented shear wave tensiometer to accomplish this goal. The shear wave tensiometer consists of a piezo actuated tapper that induces a shear wave down the tendon, which is detected by an accelerometer array. Using an anatomical model, tendon force is proportional to wave speed squared. We had our 28 total healthy young and older adults walk with the tensiometer over their Achilles tendon at 4 treadmill speed. We assumed our force decomposition based on physiological cross-sectional area. So 35% of the total force through the Achilles tendon went to the gastroc and 65% of the force went to the soleus. We coupled tendon force with muscle tendon kinematics to characterize the work done at the muscle tendon level, which is often referred to as a work loop. Since it will be helpful in explaining the results, I'll spend a little time going through the typical actions of the muscle tendon unit throughout this work loop. And for reference, the muscle tendon unit will be modeled with the symbols on the right. So first we start where the MTU is slack, about mid-swing. Then point 3 is that first portion of loading response where the foot has plantar flex, so it is flat on the ground. And after this point, the force begins to increase during the stance. From 3 to 4, the muscle is acting isometrically while the tendon is stretched. And then from point 4 to 5, the muscle is typically active while the tendon continues to stretch. At point 5, the muscle tendon unit has reached its max force, which typically coincides with its max change in length. Then from point 5 to 7, the MTU is shortening. This is where push-off occurs, and point 7 is marked as the MTU's shortest change in length, coinciding with early swing. Now for the results, I'll first show the average work loop curves for the young adults across speeds. Note that the biarticular gastrocnemius has a longer excursion because we are accounting for ankle and knee flexion. So during the first portion of mid stance from 3 to 4, the force and excursion increase similarly across speeds. So you can see in the soleus that the curves are basically overlapping for each of the speeds. However, from 4 to 5, as walking speed increases, there is a more rapid shortening of the muscle coinciding with a steep rise in force, denoted by that gray arrow. With older adults, what's interesting is that we don't see as prominent a modulation with speed at peak force and excursion. So the force is steadily increasing with excursion independent of speed. And one explanation for this is that older adults have a decreased force generation capacity at the high contraction rate during late stance. Another is that the increased tendon compliance often observed in older adults requires faster muscle contraction velocity. So it's more demanding for older adults. Both have been supported in the literature, and it's likely a combination of both factors. But what's particularly notable here is that these results would hold true even with the same muscle size. So in our healthy, active older adults, those that don't show signs of sarcopenia would still show signs of coordination changes. In fact, older adults have shown to maintain isometric strength, so these results support that older adults could indeed be losing functional capacity. From these work loops, we can also quantify the positive and negative work done, which I'll show in the bar charts for the soleus first. As you might expect from looking at the work loops, there was an age by speed interaction with negative work. So younger adults did significantly less negative work with speed, and older adults did not show any changes with speed. And then second, we saw an increase in both positive work and net work with speed. Work was significantly lower in older adults by 66%. The gastrocnemius results were similar, although we did not detect a noticeable change in negative work with speed, and net work was lower in older adults by only 36%. So in conclusion, this study shows that tensiometry can enable the characterization of subtle differences in muscle tendon behavior during walking. And our results show that age-related deficits in active stretch and shortening of the plantar flexors are evident during mid to late stance. Thank you so much for your time, and I'm looking forward to your questions.
Thanks, Anna. We have one person with a hand raised. It's James Finley. So go ahead, James.
Hi, Anna. So at the beginning of your talk, you mentioned that you computed the relative force in the tendon due from each muscle based on the physiological cross-sectional area. Did you measure this for each person or estimate cross-sectional area from values in the literature or something?
Yeah, thank you for the question. We did estimate them across all subjects from a paper by Hansfield. So we just estimated all soleus got 65% and gastrocnemius got 35%. So we measured the total Achilles tendon force.
I mean, can you maybe tell us a bit about how much variance you might expect from person to person, maybe based on the previous work?
I haven't looked at the variance specifically from this data, but yeah, that's a good question. I would expect that the results may not change too much. We did look at cross-sectional areas between the young and older adults. Older adults did show larger cross-sectional areas in the tendon, but we didn't look at the muscle level. So it could definitely be worth looking into further, yeah.
Yeah, okay, thank you.
Okay, Kirby. Kirby has her hand up, and maybe you have to unmute your mic, Kirby.
Thank you. So you mentioned that lower tendon stiffness may explain the difference between younger and older individuals because muscles have to contract faster, which limits their force production. I'm wondering, do you think a surgical procedure to shorten the tendon and thus increase its stiffness might bring the gap between younger individuals and older individuals smaller?
Great. Yeah, I hadn't thought about any like surgical implications like that. my mind immediately goes to cerebral palsy because I'm looking at that a lot, and they do a lot of tendon innervations there and surgeries, and that tends to weaken the muscle. So I would avoid against intervening at the tendon level. Maybe the aponeurosis level might be a difference, but yeah, thanks for the question.
Thanks.
Okay, Peter Adamchek, who can't figure out how to raise his hand, but
I got
wants
it.
to ask a question. Yeah.
The question is, do you think there's any possibility that the distribution of the force across the soleus and the gastrocnemius changes as the progression of the gait cycle goes along, such that it would distort the curves for the two muscles?
That's certainly something I've thought about, and I think potentially we could model. I was thinking about this, especially like, I was showing so this is a paper that was published by Emily Cooler, another member of our group. And I was looking at the EMG, so the gastrocnemius and soleus EMG timing. They are pretty aligned, so that gives me some indication that I think the forces would be the same. But no, certainly there's a lot of literature that shows there's the gastrocnemius and soleus are doing different things during the gait cycle. So that's probably something we'd need to tackle through modeling right now.
Very good, thanks.
Manoj?
Great talk. This is maybe a broader question than the specific results of your talk. I'm curious to what extent people have compared the forces measured using shear wave tensiometry with, say, muscle forces estimated using simulation techniques like, say, static optimization or something, and to what extent they compare. Do you have thoughts or comments on that?
Yeah, that's a great question. We have in this paper that I'm showing the portion of the figure for, we did compare like the inverse dynamics approach. So taking the torque divided by the moment arm and comparing that with shear rate tensiometry, and the results are fairly similar. We haven't, as far as I know, gone to static optimization, but that is certainly the next step or a step in the future.
I see. Cool. Thank you.
Okay, we'll do one last question for Emmanuel, and then we'll go to the next speaker.
So my question is regarding the tendon compliance. What sort of behavior do elder population shows, like lengthening of the tendon? Or does the lengthening of the tendon attributed to some fiber shortening due to the age-related changes? And what about the hysteresis loss if there's a tendon lengthening?
Yeah, my understanding, thank you for the question. My understanding is that the tendon does become more compliant with age. And there is support in the literature for that.
Oh, that was a fantastically concise answer. Okay, let's go on to the next speaker. Let's thank Anna. And the next person up is Shamel Fahmi from Italy to talk about soft terrain adaptation for high-Q. Shamel.
Yes, hi.
Hi.
All right, I hope you guys can see my screen. I just sent you guys a link, which is just a live stream of these slides. So usually it's more dynamic, so the videos and transitions are gonna look cooler. All right, but I keep sharing the screen anyways in case you wanna check this out. Anyways, also for more information about my talk and also the poster and stuff, you're gonna find in the link that I just put here. So if you're watching live, you can just click on it. Today, I'm gonna be talking mainly about how did we manage to make our quadruped robot, high-Q, walk over soft terrain, so that hopefully at the end of this presentation, you can get an intuition of why do we really care about soft contacts or soft terrain in the context of locomotion. This is a part of the work that has been published recently in TRO. So give it a look. Okay, so why do we really care about soft terrain or soft contacts in general? The main idea is that the world around us is not generally rigid. So we usually in locomotion controllers or in locomotion strategies, we do assume that the ground or the environment is rigid, which simplifies a lot of our problem. But generally, that's not entirely safe. And actually, this is something that has been highlighted by the Handbook of Robotics, the Handbook of Robotics, the chapter by Weber. Also, this was mentioned in one of Andrea Del Preto's talks in 2019, that the interaction between the environment and the robot, or the robot and the compliant environment, might not be safe, and it might cause some destabilizing oscillations. So why is this a problem in the area of in locomotion? Well, first, if you consider locomotion strategies, whole body controllers, for example, you're going to see that most of them are not terrain aware, which means that they often tend to assume that there's a rigid contact between the robot and the environment. So they cannot generalize beyond rigid terrain. That's the first problem. Now, the second problem comes from soft terrain locomotion itself. One, mainly because it on its own induces a lot of contact dynamics. And these two problems together causes a huge mismatch between what the whole body controller is assuming and what's actually happening in that case. And this is where the problem arises. This mismatch is what causes oscillations or might be unsafe for the robot. All right, so how can we solve this problem? Well, the first obvious thing to do is not to assume a rigid terrain anymore. So drop the assumption of the rigid terrain. You can use a more generic contact model that can account for different type of terrain. But for that, you need to understand how can you estimate, how can you feel which type of terrain you're walking over. And this is where you need to estimate that. And if we combine these two together, this is where approach comes. So with our approach, we amend the standard whole body controller with a more general contact model that can adapt to any type of terrain given its parameters, given its impedance parameters. And for you to do that, we have an online terrain compliance estimator that feeds it to the whole body controller. And then you keep on doing that in an iterative way. And we call this approach STANCE, which stands for soft terrain adaptation and compliance estimation. Here are just a couple of videos about STANCE. You can see, for example, on the right, this is just showing a little bit of dynamic motion, like a trotting gait, for example, just in soft terrain. But if you can take a look now on the left video, it's showing STANCE traversing or walking through soft terrain and transitioning between soft terrain and rigid terrain. And here you can, with that, every leg is independently adapting for the terrain below it. So for example, now you can see that the front legs are considering a more rigid contact than on soft terrain, for example. All right. So in conclusion, STANCE essentially can adapt to any type of terrain, whether soft or rigid. It consists mainly of a new formulation of the whole body controller that can adapt to any type of terrain, given the terrain compliance that is estimated by the terrain compliance estimator. Instead of talking about the results, obviously you can talk to me offline about that in the poster session, but I'm also interested here to be talking mainly about the limitations of STANCE and hopefully the future direction. So in the paper, for example, we mentioned some limitations that we can encounter in terms of state estimation and in terms of low level control, and also some fewer directions that I would love to talk about, again, about state estimation and MPC. So if you have, if any of these keywords ring a bell, just don't forget to pass by in the posters, in the poster. Lastly, this is just a slide about if you're interested these are a couple of pointers if you're interested to see what our lab is doing. We mainly work on MPC. We also work on feasibility region and other stuff also with our new robot Hubicki reel. So if you're interested, you can click on any of these if you have the live, or again, you can go to the link that I just mentioned here. And lastly, I would like to thank my co-authors and the members of the DLS lab for this work, and open for questions, and thanks.
All right. Thank you very much, Shamel. So Manoj, you have your hand raised. Is that raised from last time or for this talk?
Sorry, last time. Sorry, actually.
I didn't realize.
Or
I guess they should have a timeout on these things.
yeah, or you could pay attention.
Okay, yeah.
Or the other. Chris had his hand up. It disappeared. So Andy, you go first, please.
Okay, as a rule, why don't you do me last since I asked so many questions, but.
You are also first and last.
Okay. You're doing parameter estimation on the contact, but if you have the wrong model, maybe it matters. Or do you think like the space of all ground contacts is characterized by a spring and a dashpot in parallel, or do you think that, or does that, like, is that a rich enough model, or do you need a richer model, or what happens if you assume just a spring, but actually it's a dashpot, or it's actually plastic, or it's actually nonlinear, or whatever?
That's actually a good question. This was one of the things that we were also thinking about when we were working on stance. Well, if you take a look at the literature, you're gonna find hundreds of contact models. There are a lot of contact models. People tend to use linear springs and dampers. People also tend to use different models that are still linear, others that are non-linear. Essentially, we used the KV model, which is linear spring and damper. Going back to your question, I think it does matter. Obviously, if you have a better model for your for your terrain or for your ground, you're going to have a better result. The closer you are, the better results you get. But we also wanted something that, at least for this kind of work, that is simple, so we can test, that is fast, because we wanted to do this online. Most of the nonlinear estimation models would take more time than it wouldn't be possible for us to do it online. And so yeah, we used a simple model in here, but both of them are decoupled. So definitely improving your contact your model is going to improve the estimation and obviously the adaptation part. Did I answer your question?
Let's see. Well, it might not be true what you're saying, right? For example, the variation in the terrain from step to step might be bigger than the model error. So it might be that if you just have a 2-parameter linear model, that you have nothing to gain by having a better model. So it's not always true that a more refined model is better if there's more variation, for example, than there is in the. It's a little bit like Chris Atkinson and Pranav's discussion.
Mm-hmm.
If the variation dominates, improving the model quality is not so great or important.
Well, mm-hmm. Well, yeah, I mean, I would still think that if you have a better model for the ground and you know that it's true, you can try to plug it in. But for us also, like we managed to even capture some nonlinearity, because if you're always updating that online, so we managed to your parameter itself does change. So instead, like your K parameter is actually K of T. So even if your model is linear, your estimation can change. So yeah.
Andy, do you have an opinion about how complicated the model should be?
My guess is that for his purposes, there's so many unknowns and such variation that a 2-parameter model is probably good enough. And if he had a more sophisticated model, he'd have nothing to gain by it. That would be my guess, but I don't know.
Well, for that part, I do agree with you, and this is the main reason why we chose this. And actually, we specified that in the paper. We did it mainly because it's simple and it's fast, and for starters, that was enough for us at that time.
I'm guessing that Chris's hand raised is related to this specific conversation that's happening right now. So Chris, I'm going to ask you to join and ask your question.
All right, I've surmounted my technical difficulties. I think you need to connect this to slipping and tripping, which are in some sense far more important than any sponginess of the ground. You know, it's much more likely we're walking on sand or ice or mud than we're walking on foam. And it's very clear the system has, very fast reflexes to handle slips.
Well, I think both of them are totally important to handle to work with soft contacts, and definitely for slipping. It's just for me.
But you have a friction coefficient in your model, probably.
Yes.
Also.
Yeah.
So he said 2 parameters. It's really a 3rd parameter that's already in there.
I mean,
But
So-
friction is a terrible model for sand or lots of stuff, walking in a forest, things where you punch through something. I would
totally agree.
argue you got to have a unified model for all this stuff that with 50 milliseconds of data decides what to do.
Mhm. For me, it's a little bit mix of what Chris and Andy said. So yes, as Andy was mentioning, that the rest of the formulation of the whole body controller does take into account of slippage, or including the friction constraints. Going back to what Chris was mentioning, is that this might not be enough, and that you want a more general model. And for that, I think, yeah, that would be something cool to actually start thinking about. But for me, at least for that work, I was interested about soft contacts. There are other people in our lab that are working in slippage, for example. So I think it's a matter of what research question are you working on or solving or asking.
Okay, fantastic. Thank you, Shamel. We're going to move on to the next talk. The next speaker is Christian Hubicki. He's at the Florida State University. Christian.
Well, thank you so let's see. All right, thanks so much. Can everyone hear me? Everyone see me?
Yes.
See the talk. Thank you so much. Anyway, thank you all for having me. I appreciate it. And thanks for all the organizers for being so flexible given the whole pandemic going around. So I'm from Florida State. I'm Christian Hubicki. I'm be talking about risk-constrained planning for robot locomotion. I'm from Florida State University along with some of my colleagues, but that's the one in Tallahassee, in case you didn't know. All right, that's not the Gainesville one, it's the Tallahassee one. And down at the Optimal Robotics Laboratory, which is my lab, where we deal with like dynamic locomotion. This is our Cassie robot, who people have seen the Cassie Agility Series robotics before. But of course, down at Florida State University, ours is the Tallahassee Cassie, obligatory branding. So, and we're working on our own controllers for dynamic locomotion and stability in terms of uncertainties, efficiency, all the usual stuff that you guys love so much, and I do too. So, but today I'm going to be talking a little bit about part of a collaboration that I've long-standing collaboration with Monica Daly, and she and guinea fowl locomotion, where she will study how guinea fowl runs over obstacles. And you might wonder, well, why am I involved? Because this is my research subject. That's me with my research subject right there, looking equally poised. And the answer is trajectory optimization. Many people talk about it today. You've saved me a lot of trouble. Thank you all so much. People also talk about it in terms of motion planning or optimal control. I'll use the term motion planning a lot for a lot of this talk. Particularly, I use trajectory optimization in the past for robots like this to come up with a walking gait that's as efficient as possible. So like if we try to come up with a walking gait that minimizes cost of transport, it'll spit out these joint trajectories, and that'll be a core part, just a part of a controller that makes the robot walk like this on a treadmill, okay? Can people see the videos okay, by the way? I'm not sure I do the fantastic. Reduced order math models, but I do it instead with Monica using reduced order math models and optimization. And so I'll take a sort of sling-loaded inverted pendulum-like model with actuation, and then optimize it with respect to some control priorities, which I love to cartoon with this technical schematic right here. Often we care about things like energy costs is what we'll optimize for, and we'll get results that look something like this, okay? Where you'll have like a running motion like that, or an optimization that'll run around a path. And we'll actually want to make it line up with real bird data like this, okay? And that bird data comes from studies running around bends and over obstacles and things like that. And one thing Monica and I noticed is that this bird, when it's running around, has to deal with a lot of stuff, a lot of sources of risks. For one, it's slippery. Whoop. You can see a little slip right there when it goes by. It has to run around a bend and not run into the wall, but also has to worry about the greatest source of risk of all, which is the experimenter. Okay, so you got to worry, make sure that you're not getting too close to him because he looks dodgy. So this has really pushed us in the direction of the idea of locomotion as the optimal task completion, subject to acceptable risk probabilities. And this is something we're just starting to explore now. So this is a little on the preliminary side, but this is what I want to put out there. Okay, and this is something we care about in robotics too, because there's all kinds of sources of risk in robotics. You could break your legs. There's uncertain friction that may or may not make you slip. There could be a random agent going into your midst that you want to make sure that you don't run into when you're completing your task. So the idea is to be able to do trajectory optimizations traditionally and constrain the probability of risk. Okay, the probability of failing. And so imagine this here is your traditional your traditional trajectory optimization problem, where you want it to do a thing, and this is what it can do. So these are things that can be done, but we constrain it by saying this is the acceptable risk tolerance, and this is the amount of space that we have that actually allows us to complete the task without failing too much. So just as a quick example, that's a little bit more concrete. Let's look at a coin flip. Okay. So let's say your robotic task was to flip 5 coins, and if it ever comes up tails, you fail. I'm sorry. Okay. So really simple math for computing that is you have a risk of failure probability, which is R, your risk, which is equal 1 minus your probability you'll survive, which is equal to 1 minus a half times a half times a half times a half times a half, gives you 97% chance you'll fail. It's bad. And if that's greater than some acceptable risk tolerance RA, then you're in trouble. The optimizer has to consider something else. So let's not just deal with just coin flips, let's deal with functions where delta here is instead of being just some flat number, is dependent upon system variables like your states. It could be the temperature, it could be the amount of force in your leg, it could be getting too close to the experimenter. And you have a probability of failure that's dependent upon that parameter that you define. And one thing we found is if you start taking the log of this, you start to get these piecewise linear curves, which are pretty nice because when you can actually reformulate them in optimizations to have piecewise, so that you can have linear inequality constraints, which is nice because this can actually make nice linear constraints, and it doesn't slow the optimization very much, which is great. So technically, that's nice. And so we try to demonstrate this on robotic locomotion with a simple robotic hopper. We'll try to get it to go as fast as possible. This is an example of it jumping around, going at a pretty high speed. But we did it with having a limit on how much leg force it would apply. So if you optimize it normally with 0% risk, it'll say, I can only go that much force. But if you tell it you can accept some risk, you can go higher forces. As a result, go a bit faster. You can see it's only about 3 meters per second at the fastest speed. So we allow it more risk, it does more. Nice proof of concept, in my opinion. But you might be thinking failure probability functions. What the heck do I do with that? How would I even know what that is for my robot? That's a great question. How would I even define it? And I'll end with some tease of what we're working on now, which is the idea of learning them through a few failures. Okay, and so this is an example that Jacob Hackett whipped up. He's here as a great undergraduate student, and we put together this toy model task of having this little agent avoid the scary dog while having to get to there. And so the idea is it tries to go into the dog's radius and it bites it, and that's bad, and it learns to fit the risk function with just 5 iterations. So with that, I kind of want to leave it there. I'm sure there are a lot of details that we can fill in. I also want to point out, I'm not the first person to talk about risk and optimizations, not by a long shot. I mean, the financial people alone, they love this stuff, right? Or they have real dollars counting on it. And I have lots of takeaways here that we can talk about during the questions. But I think the one I think is most interesting is the idea of it learning risk while it's actually out in the field, and then learning not to touch the hot stove. I think that's a cool idea. But I'd love to take your questions, and thank you all for your time.
All right, thanks, Christian. I've decided that it's worse to have the sound of one pair of hands clapping than none. So
well, I
just
appreciate
imagine 245 hands clapping.
Oh, thank you very much.
Shai.
Hi, Christian. So this is lovely, and I think it's long overdue in our world. So thank you for doing this. if you've looked at the financial literature, you probably know that they have this notion of coherent risk estimates. And I was wondering as to your thought of which kind of risk estimate is the relevant one for locomotion.
So I'm going to be honest in that I'm still looking into the financial side of it. I got a nice textbook from an actuary friend of mine just last week, so I'll look at that more. But if you in order not answer your question, because I don't know a good answer for it, so I hate to mislead you on my opinion. I am mostly just dealing with some kind of functional estimation of failure that's dependent upon state. But I would love to hear any suggestions. It sounds like you've looked into this quite a bit. This is, by the way, I should say, Jacob is awesome here. He did this in the last like 3 to 4 months. So yeah, so so we are open to hearing what you have to say, Shai. So I'd love to catch up with you afterwards. Sorry to punt.
I have to do that. Okay, great.
Sorry to punt. Okay, Ryan.
Yeah, hi, are you able to hear me?
Yes, I can.
Yes.
Great. Yeah, really awesome talk. I like the concept of it all. It's great. My question is there a reason why you're thinking about acceptable probability of risk as a constraint versus, just another term in your cost function? Why not optimize to minimize your risk?
Perfect. I love that question. We think about that a lot. And the reason is, and this part is philosophical, that anything I put in the objective function, I absolutely want to be minimized. And honestly, in legged locomotion, it tends to be energy cost. That's where we tend to go. So like technically the objective in a lot of these optimizations is energy cost. And so, and technically speaking, when you're actually implementing these robotic trajectories, you want to minimize for some kind of cost, because if you try to literally maximize or minimize risk, it'll go to extremes that tend not to be optimal. Now, but that's the robotics angle. But the biology angle, I think, is more interesting, because this, to me, because one thing in biology we care a lot about that we all kind of know when we do these experiments is that every individual is different in how they behave. And we're trying to find a decent way to model that. And one thing kind of notice in the bird that some of the birds are more risk averse than others. They're more careful. So I want to be able to have a dial in terms of acceptable risk tolerance that says, brave bird, or shy bird. You can kind of see it with this, with this dog thing right here. That you can see the frankly suicidal puck here and the very scared puck.
Christian, but I think you can think about it probabilistically, right, where it does become part of the cost function, rather than say minimizing expected value of cost. Mm-hmm. Right, you're thinking about including some higher order moments, which inherently bring in notion of risk. As opposed to as a hard constraint, I think, like the last person asked.
So you're saying, so you're asking like why not just have a term in the objective function? Is that what you're implying, Michael?
Yeah, but I think the natural thing what people do is to say like we're going to minimize some expected value of cost, right? But that it ignores essentially risk. And then you can start adding in higher order moments, like you add in standard deviation, you add these terms which bring in some notion of risk tolerance.
Totally agree, and that in a way is a little, maybe I'm misunderstanding, is a little orthogonal to the question of risk. It's like that's like uncertainty in the cost, or like the different worlds of cost that you would have, and you have the expected value. Yeah, you could have that completely. That could be your new objective function, but that's almost a separate question of where you put risk. Do you put it as an additional term in the objective or in the constraints? If I understand you right, Michael, and I may not. Thank you. Thank you for the question. That's a wonderful question. Anything else?
Yeah, thank you. I'm going to take Andy's recommendation and shift him to last and let John Dingwell go. In fact, Andy, I'm not even going to let you ask a question this time. And if you're okay with that. And
sorry,
John beat you.
But I had sort of two quick things. One, I guess, do you make a distinction in terms of a difference between minimizing risk versus simply avoiding risk? And maybe that's what Michael was trying to get at in terms of how you might be able to incorporate. Because I agree, if it's just minimize risk and drive risk to zero, that's probably not what biological systems try to do.
Sure.
Simply try to avoid risk, which might be, but maybe you could fold that into a cost function in a different way than simply minimizing whatever you're going to quantify as risk.
Yeah.
The other thing I was going to mention is that there is pretty good literature in older adults and falling, that there are different categories of older adults. There are people who fall because they are too risk averse. And there are separate people who fall because they are not risk averse enough, if you will. There's actually a paper, I think the title includes the phrase something like type A personality as a risk factor for falling. So people who underestimate their own abilities, or no, overestimate their own abilities, underestimate their own limitations, go running around doing crazy things they shouldn't be doing, and they fall because of that. So there is a distinction in the falls literature related to that as well that might come into play here.
Thank you so much. Thank you. That's really appreciated. We'll chat more about that. Thank you. Anything else? We all done now, Max? I release everyone from my captor. Okay, from my captivity. Okay, thank you.
Yes, thanks, Christian. We'll move on to I believe it's the final talk.
Thank you all.
Jan,
I'll stop sharing.
You're up. I'll introduce Jan Stenum, and his talk is about step time asymmetry, and from Johns Hopkins and University of Florida, I guess. Jan.
Thank you. Let's see here. Can everybody hear me?
Yes, we can. We can see your screen. You are good to go. All
excellent.
Go.
Thank you. Let's see here. All right, so this study or project really began with an interest in the relationships between gait asymmetry, energy cost, and energy optimization. So we know that gait asymmetry is common in certain gait pathologies like hemiparetic or amputee gait. And it's also true that these have increased energy cost compared with the gait of healthy adults. So asymmetry is often assumed to be detrimental in part because of these expected relationships between gait asymmetry and energy cost. The cost of asymmetry has been demonstrated in healthy people instructed to walk asymmetrically. And this study here nicely showed that there's a cost of asymmetry in healthy people. Now, an alternative view is that asymmetry may be functional in that it may be adopted if it is energetically optimal. So we wanted to test that idea using a split belt treadmill. So a split belt treadmill has two belts that run side by side, and they can go at different speeds. After an initial training or adaptation period, the gait pattern resumes a steady state pattern with about symmetric step lengths and asymmetric step times. Here, asymmetry is calculated as the difference in the value of the two steps of the stride cycle divided by their sum. And we then wanted to test the hypothesis that the adapted steady state asymmetries and step times and step lengths were energetically optimal. And we did that in three conditions that all had an average belt speed of 1.25 meters per second, but then with increasing speed differences between the belts at 0.5, 1, and 1.5 meters per second, all of them around that average belt speed of 1.25 meters per second. We recruited 10 healthy young participants that came into the lab on 3 days, one for each of the speed difference conditions. They first walked symmetrically with belts tied at 1.25 meters per second. Then they performed an adaptation period with belts split. And from that, we found the preferred asymmetry. And then after that, they performed a series of cost mapping trials. And those were partitioned into one set of cost mapping of step time asymmetry, where step time asymmetry varied around the preferred value, while step length asymmetry was enforced to be symmetrical. And a cost mapping set of step length asymmetry, where step length asymmetry varied around symmetry, while step time asymmetry was enforced to be constant at the preferred value. We played the beat of a metronome that was set to each participant's preferred stride time in normal tide belt walking. In front of the screen we showed visual feedback of step time asymmetry and foot placements so that we could indirectly enforce step length asymmetry. And we used expired air analysis to get a metabolic cost that we calculated as the net metabolic power of split belt walking relative to its value in tide belt walking. So when we go ahead and look at the values of the preferred step time asymmetry, we found that those increased with greater speed differences between the belts. When we look at the cost landscapes that the cost mapping of step time asymmetry produced, we find that those look qualitatively similar with clear optima between the speed difference conditions. And when we compare the optimal with the preferred step time asymmetries, we found that the preferred step time asymmetries were energetically optimal across all the speed difference conditions. So that supports the idea that humans will adopt an asymmetric gait to optimize energy cost. When we next look at the preferred values of step length asymmetry, we find that those are not different between the speed differences. And when we look at the cost landscape that the cost mapping of step length asymmetry produced, we find that those are similar in the left-hand portion of the curves with negative step length asymmetry in that they decrease, but they are different between the conditions in the right-hand side of the curves with positive step length asymmetry, so that the 0.5 meters per second speed difference increased to form a U shape. The 1 meters per second difference increased moderately, and the 1.5 meters per second condition plateaus. When we compare the optimal step length asymmetry estimated from the cost landscapes with the preferred, we find that those are not, or we find that the preferred is not energetically optimal. So they're different from the optimal, which suggests that the preferred step length asymmetry is not selected to optimize energy cost. So to wrap up here, we find that the preferred step time asymmetry in split belt treadmill walking was energetically optimal. That supports the idea that humans will adopt an asymmetric gait to optimize energy cost. And that may suggest that the asymmetry in pathological gait may be a functional adaptation in order to walk economically. It's worth noting that only temporal gait asymmetry was associated with energy cost, but spatial was not. So there might be distinctions in the relationship between gait asymmetry, energy cost, and optimization for temporal and spatial asymmetry. And last, it's not clear how these effects would generalize to pathological gait and overground walking. So we think that that may be a fruitful area to continue this line of research.
All right, thanks very much. That's 238 hands clapping. Please raise your hand if you have a question. And maybe I just want a clarification question to start with. So how long were people allowed to adapt to each condition?
So the adaptation period in itself was 10 minutes. I will say that we brought people in for a training visit so we played the beat of a metronome. We showed 2 types of visual feedback. That's a lot. So we brought in people for a training visit. So they had prior experience with split belt walking from that, about an hour. And then the accumulated split belt experience from the previous visits. From day 1, they had about 1 hour of split belt experience, day 2, about 2, and then 3 hours all in all. But adaptation period itself was 10 minutes.
And then remind me, what was the average steady state step length asymmetry? Like around 0 or?
Yes.
Yeah. We've recently done work led by Natalia Sanchez where like with long periods of time, people adapt to positive asymmetries, which is what you're showing to be energetically optimal. So those are 45-minute adaptation periods, and they're still adapting even after that. So that might be one of the explanations for why the people didn't prefer positive step length asymmetries was the shortened adaptation period.
Yeah.
Okay, so let me go Peter first, and then we'll do you next, James.
Right, so is that James Finley is coming next? I was just going to plug his results from a couple of years ago and ask if you've studied the mechanics of these apparent metabolic optima and found some sort of match to the ability to, say, harvest energy from the treadmill. But I'll defer to James's question before that gets answered, because I think he's going to explain it better.
Okay, James, you're up.
So I was not necessarily going to explain our results. I mean, so I think Jan is aware of those results, showing that people can, acquire work or require energy or assistance from the treadmill for these positive asymmetries. And that, in our work, we really focused on step length, foot placement, whereas you seem to focus a little bit more on this timing issue. And one thing that I'm interested in getting your perspective about is, what is it about the timing that relates to mechanics and then energetics? So what is that, how might you explain the relationship that you found here and the patterns that you observed?
Yeah, so in terms of so we've also done a study with effects on asymmetry and overground walking. And there we find step time asymmetry to have greater effects. In terms of the mechanism linking the kinematic asymmetry to metabolic energy consumption, we did look at work performed on the center of mass. And we found that redistribution of work from push-off to single support explained quite a lot of the increase in metabolic cost with asymmetry. That mechanism also explained the step length asymmetry cost. So in terms of a clear distinction, I'm not really, I don't think I have a good answer for a clear distinction, but that mechanism seems to explain both of these pretty well, actually. I will say that was not in split ball walking. We have not looked at the mechanics of that yet.
Halsey? Were you satisfied, James?
Yeah, that's fine.
Hi, Jen. Thanks for the nice talk. It's more of a clarification question. I didn't quite follow when you were doing the landscape for step time, what are the different targets of step asymmetries that you were imposing on people? I wanted to ask you if those were during tide walking, those different step times, or if those were during split walking. That I was confused about that. And then the second thing is, how good were they? Like, were the subjects able to accomplish the task of like meeting the step time targets that you were giving them?
Yeah, you can still see the slides, right?
Yeah.
Yes.
In terms of how well, it's a little bit hard to see. I didn't include the kinematics of the cost landscape, but you can. It's actually not that easy to make it out. But they were able to perform what they were instructed to do fairly well, I would say. I think that was your last question, and you had questions before that. Could you?
The first one was, so when you said they did it very well, so I assume you have some metric of accuracy that, some figure somewhere to quantify that. So, but I believe you that they were really good. Now, the second thing is like whether they were doing this during tide walking, like when the two belts move at the same speed, or split walking. I was confused about that.
Oh, so that was all on split. In the tide belt scenario, we did enforce step length and step times to be symmetrical, but so that the cost is expressed in relative terms based off of the cost during normal tide belt walking, symmetric step lengths and step times. But they did not do this cost mapping in tide belt walking. We have another study where they did do that, but that we have not related the two.
Okay, thank you.
Andy.
I have one just really basic question, which is the kinematics of the belt is really hard to think through. And just a second, I can't think it all the way through. And superficially, you'd think that the time, like you said in your experiment, you controlled step asymmetry with time asymmetry. Are those independent variables, or does one determine the other?
In terms of
just the basic kinematics, like what you're stuck with.
So they're all related. Like in terms of the control, that's not really what we're interested in here. We did a big chunk of setting up, planning, designing this experiment was just understanding how these are related in order to understand how we needed to enforce where they place their feet in order to get at the desired step length asymmetry. But with a change in step time or step time asymmetry, that is going to influence step length asymmetry unless you correct for that with differences in where you place your feet. And understanding that was.
But there's still some freedom. I mean, I just can't think it through fast enough. They're not. One doesn't fully determine the other.
No.
At a given belt speed, they're independent. Is that correct or not correct? Max is nodding his head.
Yeah, it's correct.
Which is correct. They're independent.
They are, yeah.
They're independent.
Yeah, you can change one without changing the other.
But it will require compensation in certain gate parameters. Yeah.
I have a follow-up to that. I think it would be, honestly, it would be really interesting to see for what is the step length asymmetry for these different step times, that because I don't think they are independent, or at least I haven't seen that. Like whenever you are altering a step time, the step length asymmetry is also affected. So
so we did in pilot tests for that. We only enforce step time, and we let people place their feet however they wanted. And you do see that there's a proportional relationship between step time, when that is experimentally enforced to different values. Step length asymmetry will vary proportionally together with those changes in time asymmetry.
Okay,
but that was.
I hate to cut it off, but I do need to. And there's still a lot of hands raised. And so I encourage via Slack for you guys to figure out how you can side chat on spatial chat or what have you, including the hand raise of Natalia Sanchez, who has deep insight to these kind of things. But we do need to move on to the next speaker. So thanks very much, Jan. And I guess people were thinking maybe there wasn't a next speaker, but there is. And that is Romeo, who due to technical problems was cut off last time. And so Romeo, if you're there.
Hello, can you hear me? Hi Max, can you hear me now?
Yes, hello Romeo. Let's give it another shot. So when you're ready, fire away.
I won't turn my camera on this time in the hope that will make a difference. Is that okay?
So far so good. Let her rip.
All right, so I'll start then. All right, so yeah, I'm Romeo Orsolino. I'm from the Dynamic Robots Systems group of the Oxford Robotics Institute, and today I'm going to tell you about two projects I worked on that both aim to provide to improve the feasibility and the reliability of the motion plans obtained with offline nonlinear trajectory optimization, so that they can be successfully executed on the robotic hardware. Both projects are based on the Trajectory Optimization for Working Robots library, published by Winkler 2 years ago, that many of you might know. This library allows us to transcribe a locomotion problem into a nonlinear program through direct collocation, which can then be efficiently solved with a third-party solver. The advantage of this library is given by the minimal parameterization based on the single rigid body model, which allows us to simultaneously optimize footstep locations, base poses and base linear and angular velocities, contact forces, phase durations, and even fit sequences for quadrupeds, for example. This parameterization is minimal, but still generic enough to enable the formulation of different gaits in arbitrary complex scenarios. The limitations of this library consist of an overall lack of robustness due to the presence of multiple local minima because of the nonlinearity of the problem, and also due to the fact that the original formulation is only meant to solve and find feasible solutions and not optimal solutions. And then, despite the excellent computational performances, it's still not good enough for online motion planning. And yeah, these 2 points together lead to a difficulty to deploy the obtained trajectories on the hardware. So in order to increase the robustness, there are, I can see mainly 2 ways. One way is by increasing the success rate. And this can be done by including feasibility constraints such as the motor limits into the formulation, or to other constraints like the shin collision avoidance and the safety of the footholds, or minimizing the base acceleration. And this was a focus of one project I performed with a student of mine at IIT that I'll talk about. Another way to increase the robustness is to decrease the convergence rate and try to achieve online planning. And this was the topic of another project that I recently joined at Oxford that achieved that by developing a neural network that can learn initial guesses for the NLP program. So as regards the first way, the success rate, I'll focus on the motor joint torques. And in particular, the first project I mentioned proposes an approximation of the force polytopes. So the yellow box you can see on the top left corner of the slide is the set of admissible joint torques. And that can be mapped into a set of admissible contact forces at the end effector of the robot. The problem with that mapping is that it's configuration dependent. So it requires the knowledge of the full dynamic model of the robot. For this reason, we propose an approximation of the force polytope that can be seen as the red polytope in this figure, that is obtained as a morphing of 2 reference polytopes. The green polytope, which is the one obtained at the maximum retraction of the leg, and the blue polytope, which is the one obtained at the maximum extension. So given those 2 polytopes and the position of the foot expressed in polar coordinates, you can obtain the approximation of the first polytope. Alongside with this first polytope approximation, we propose also the addition of the other feasibility constraints that consider the foot size and the shin collision in the problem. And here you can see a video of IQ simulation that attempts to execute a trajectory that was computed offline with the baseline tower library. And because it doesn't consider the foot size, it fails. But as you can see, thanks to the inclusion of the constraints I mentioned to you, we were able to have IQ walk up this palette. So this work is going to be presented in ICA this year. And I will switch to the second point I mentioned in the introduction, which was the convergence rate that can be improved with warm starting the trajectory optimization problem. In this work that is also going to be presented in ICA this year, in particular, we propose a neural network that learns offline in a supervised way, a mapping between initial robot poses and trajectories that can be used to initialize the problem. 4 fixed tasks, which are composed of fixed terrain, fixed base goal and feet position for a fixed number of steps and for a fixed total duration. Thanks to that and to the analytical costs that we propose that minimize the base velocity, that regularize the feet position and minimize the amplitude of the contact forces, we were able to achieve a 95% success rate within just 10 solver iteration. And the number of iterations that it takes to the solver to converge to an optimal solution is now 5 times lower than those problems which were initialized with the baseline heuristics. So here are some examples of tests we performed on the robot. You can see a trot on a flat ground, and then the robot walk up 2 pallets of 16 centimeters. This would have not been possible without the significant increase of robustness obtained by the analytical costs and by the offline supervised learning that allows to discard local minima and only deploy to the robot the best trajectories. For example, this motion lasts 7.5 seconds and it took less than 2 seconds to obtain it. So now that we are able to achieve such a high success rate, the next obvious step is to go towards continuous replanning. So in this slide, you can see 5 freeze frames of the robot while stepping on the pallet. And at each of these time instants, we can run a nonlinear trajectory optimization problem that reoptimizes the walk and allows the robot to react to possible unexpected events and also to interact with the direction commands of the user. So if we stack together the individual plans, we can obtain the cumulative plan that represents the trajectory of the robot from start to end. So I'll conclude by showing you this video where you can see a visualization of the trajectories optimized online in an MPC fashion for animal. On the left, you can see the operator sends different forward velocity commands. And on the right, you can see the robot that follows those commands and interacts with the user. So yeah, that's all for my talk. Thank you very much for your attention, and I'll be glad to take your questions now.
Fantastic. Thanks, Romeo. Please raise your hand if you have a question. Joe.
So I've noticed from playing around with the different outputs from Tower that you can get some pretty dynamic motions, more than what we're seeing here, different like flying trots, jumps, those sorts of things.
Yes.
But I still haven't seen any of that on the robot. Is this working towards that gap, or is this something else entirely?
Yeah, well, that's the direction. I wouldn't say that we are attempting to try the most dynamic motions you can get out of Tower, but at least we want to retain the possibility of optimizing different type of gates and adapting the timings while we navigate through, as complex scenarios as possible. I wouldn't say that the most dynamic motions you see in Tower are actually feasible on the robot, and probably not even in simulation.
Okay, and you don't think that's due to these robustness issues? There's something else there?
Well, it's definitely due to these robustness issues. The first point being the joint torque limits I mentioned before. I don't think let's say the vanilla library considers that. And then, of course, there might be issues regarding the contact modeling that is pretty simple, let's say.
Okay, I think we're gonna draw to close there. Thank you very much, Romeo, for trying that a second time. It was, we all benefited from that. And I think we can all agree that session 2 has been the best session so far, and will probably likely be better than session 3 and session 4. So you guys got to step up your game a little bit, I think. And we'll see you back here in half an hour for that, I believe.
So actually, Max, we'll spread the overage out a bit. So rather than only having half as much time as we expected, we'll sort of split it. So we'll come back at 3:15 Eastern time. So that's 45 minutes from now to sort of split the difference here. I know you're all shocked to see that we are over time here. A quick note for anyone watching on the YouTube stream, we do have a separate stream video for each session. So go back to the sort of user page and click on the new session when that starts around 3:15.
Aaron, quick question for you. Do you is there an automatic way for the talks to end up on YouTube, or is that there's some days and days of delay for that?
I think they are, but if not, we'll try and get them up as soon as we can.
I don't mean live stream, but like we can go back and look at talks from this morning.
I'm pretty sure that is the case.
It's actually there's it still thinks that session 1 is live and it's not, so there's that confusion. But if not, then I'll try and get them up as soon as possible. But right now you can go click on session 1 and see what you missed back there.
Very cool, awesome.
So just to clarify, so where is the same place we go for speakers afterwards to talk to people? Is that where we go or something?
Yeah, so for this break, there's the 8 poster sessions that are going on simultaneously in rooms 1 through 8. Room number 9 is sort of the spot to catch the speakers that just talked in this session. Try and catch them for follow-up stuff in room 9. And then room 10, there's nothing specified. So if you're looking for an empty room to go chat with someone, head over there. There's always Slack for asynchronous communication. And I'm going to paste the Zoom chat here into the Slack channel for speaker session 2, because there were lots of good questions going back and forth there that we don't want to lose. All right, I'll see everyone back in about 45 minutes.